steel. It's everywhere, isn't it? I mean, you think about our buildings, cars, infrastructure. It's fundamental.
Absolutely fundamental, but it comes at a cost, a big environmental
Yeah,
cost.
that's the thing. Almost 2 tons of CO2 for every ton of steel produced. That's huge.
It really is. And about, what, 9% of all human-caused CO2 emissions globally?
Mm.
It adds up fast.
Okay, so let's really unpack this today. We're doing a deep dive, focusing specifically on one key piece of research you brought to us: trends in the global steel industry, evolutionary projections, and defossilization pathways through power to steel.
That's the one. It lays out a lot of the current thinking and future possibilities.
Right. And our mission here is to pull out the crucial insights from this study.
Right.
How can the steel industry actually, decarbonize? How does it get in line with Paris Agreement goals?
Exactly. Looking at the pathways, the tech, the energy shifts needed, all based on this analysis.
So where do we start? The current state, I guess?
Yeah.
This study paints quite a picture of growth.
It does. I mean, think about it, from 200 million tons back in 1950 to over 1.9 billion tons in 2021. Just immense growth.
And the study mentions efficiency gains, right? Something like 60% less energy used over 50 years.
Yeah, energy intensity is down, which is good. But the carbon intensity, that's stayed pretty stable, according to this study.
So less energy, but still roughly the same amount of CO2 per ton of steel.
Pretty much. It tells you efficiency tweaks alone aren't cutting it. We need a fundamental process change.
And the total emissions figure for 2019 mentioned in the study.
3.4 gigatons of CO2 globally. A massive number.
Okay. And how is most of the steel actually made today? The study breaks it down, right?
It does. The dominant method still is the blast furnace route, BF. That's about 75% of global production.
75%, wow.
And usually that's paired with a basic oxygen furnace, so BF-BOF. That whole configuration was also about 75% in 2020.
Okay, so that's the main way. What's the other chunk?
The other 25% or so is the electric arc furnace route, EAF.
EAF. And this study notes that's different because...
Well, the EAF can use recycled steel scrap, or it can use iron ore that's been processed differently through something called direct reduction.
Right, direct reduction. We'll probably come back to that.
Yeah.
But the energy use difference is interesting here.
Oh, hugely interesting. The study highlights this really clearly. BF-BOF uses a lot of thermal energy heat, basically, around 7 milliWh per ton, and a tiny bit of electricity.
Yeah.
EAF using recycled scrap, much less thermal energy, only half a megawatt hour, but it needs way more electricity, about 3.7 milliwh per ton.
Ah, so shifting to EAF means shifting towards electricity demand.
Exactly. It really points towards electrification being key for efficiency, potentially.
And geographically, this study points fingers, doesn't it? Or rather, points out concentration.
Well, yeah. China is the giant here. Over 800 million tons a year. That's almost half the world's steel.
49%, the study says.
Right. So obviously, China's energy use and environmental impact from steel is enormous internally.
But also a huge potential lever for change if they adopt cleaner tech.
Potentially, yes. That concentration could be an opportunity.
And the study also mentions where steel goes construction mainly, with long lifespans.
Yeah, stuff that lasts decades, centuries even, which affects recycling.
How so? The recycling rate is actually pretty high, isn't it? 81% overall.
It is high, yeah. And recycled steel makes up about 30% of the raw material input. But because things like buildings last so long, you can't just rely on scrap to meet all the demand, especially growing demand.
Right. So high production, carbon-heavy process, recycling helps, but isn't a silver bullet.
That's the picture.
And this study, trends in the global steel industry.
Huh. It's pretty blunt that current methods just won't meet climate goals, right?
Absolutely blunt. It mentions projections, like from Eurofer.
The European Steel Association.
Right. Even with the best current tech, they only see maybe a 15% CO2 cut by 2050.
15%. That's
Okay.
nowhere near net zero.
Not even close. So we need something radically different.
Which brings us to the alternatives this study focuses on. What are the main contenders? The study really zeroes in on two main pathways: hydrogen direct reduction, HDR, and something called electrowinning, or EDUMWay.
HDR and EWine.
Yeah. These are the core of what the study calls the power-to-steel model, shifting from coal to electricity and green hydrogen.
Okay. What about things like carbon capture, CCS? Does the study mention those?
It acknowledges they're discussed elsewhere, CCS and BECCS, that's with bioenergy. But this study points out their limits. They don't get you to zero emissions necessarily.
And issues like cost, complexity.
Exactly. And for BCCS, where do you get enough sustainable biomass? So the focus here is really on HDR and EDUMWay as the main routes to deep decarbonization.
Okay, let's dig into HDR first then. Hydrogen direct reduction. The study seems quite positive about this one, especially near term.
Yeah, the DR plus EAF route is seen as a good step because fundamentally it gets rid of the coal. You're not using coke anymore.
Right, and this study mentions even using natural gas methane, CH4, instead of coal in the DR process.
Yes, and that's already done industrially. It's not zero carbon, but the study says it gives you about a 35% CO2 reduction compared to the old BF-BOF route. So it's a significant step.
But the real prize is using pure hydrogen, HDR.
That's the ultimate goal discussed here, yeah. Using pure hydrogen produced cleanly, that could potentially get you to zero carbon steelmaking.
And this isn't brand new, apparently. The study mentions a commercial plant back in '99.
It does, yeah, in Trinidad and Tobago. Though back then, the hydrogen itself was still made from fossil fuels, from methane.
Ah, okay. So the key now is green hydrogen.
Precisely. Made using electrolysis powered by renewables. That's the focus now.
And how does the HDR process work, according to this study? You need an electrolyzer.
Basically, yeah. The study outlines it as integrating an electrolyzer with the existing DR plus EAF setup. The electrolyzer makes the hydrogen.
Using clean electricity.
Hopefully, yes.
Yep.
And then that hydrogen is used instead of gas or coal to chemically reduce the iron ore. Then that reduced iron goes into the EAF to make steel.
And the energy numbers. How much electricity does this HDR route need per the study?
It estimates around 5 to 5.5 megawatt hours of electricity per ton of crude steel.
Okay, that's quite a bit more than the EAF recycling route, but potentially zero carbon.
Right. And most of that electricity, the study notes, is for making the hydrogen itself. It estimates needing about 51 to 58 kilograms of hydrogen for every ton of steel.
So a big demand for green hydrogen and the electricity to make it.
Very big demand.
What's the timeline look like for HDR in this analysis? When could it be mainstream?
The study seems, well, cautiously optimistic. It calls HDR the most developed green steel process, suggests it could be ready for broad implementation from 2030 onwards.
2030s. Okay, and pilot projects are already happening.
Yes, quite a few are underway or planned. There's real momentum there.
All right, let's switch gears to the other big one mentioned.
Electrowinning.
EWIN. This sounds even more futuristic.
It is a bit more out there, yeah. Still more in the research phase mostly. But the potential payoff, according to this study, is huge. Maybe up to 98% CO2 elimination.
98%. How does that work?
Well, the study describes it as electrodeoxidation, basically using electricity directly to separate oxygen from iron oxide.
Okay.
It happens in a liquid alkaline electrolyte solution, and importantly, at much lower temperatures than traditional steelmaking, like 70 to 114 degrees Celsius.
That's a surprisingly low temperature.
Yeah.
And the electricity needed.
The study's initial estimate is about 3 megawatt hours per ton of iron, but then you still need an EAF to turn that iron into crude steel.
Ah, right. So the total.
Total electricity comes out to around 5.2 megawatt hours per ton of crude steel in this analysis, so similar ballpark to HDR, actually.
Interesting. But it's further off in terms of readiness.
Definitely. This study suggests maybe industrial scale around 2040 at the earliest, though it does mention some industry optimism for sooner, maybe 2025, 2030, but that seems ambitious.
Yeah, 2040 feels more realistic for something still mostly in R&D.
Agreed. It's promising, potentially very efficient, but needs more work.
Okay, so we have these potential tech pathways, but how much steel are we actually going to need in the future? Does the study project demand?
It does. It uses a GDP-based model. Projects growth from 1.6 gigatons in 2020 up to about 2.4 gigatons by the year 2100.
Still growing then, quite significantly.
Yeah.
How does that model work? Based on GDP per person?
Essentially, yeah. It projects steel production per capita linked to GDP growth. It uses a specific equation.
A Fourier equation, the notes say.
Right. It basically models a curve, like rapid growth as countries build infrastructure, then it levels off as economies mature, maybe even declines slightly per capita later on.
And it aligns these projections with UN Sustainable Development Goals.
Yes, the GDP and population forecasts used are consistent with those UN resolutions, according to the study.
And what about recycling's role in meeting that future demand?
That's modeled too, and it's really important, based on historical data, product lifetimes, recovery rates.
Like how long buildings or cars last before the steel can be recovered.
Exactly. And the study projects the share of recycled steel will keep growing, potentially stabilizing around 89% of total input by 2100.
89%, that's huge. So mostly recycled steel eventually.
Eventually, yeah. Largely because of all that steel already locked up in long-lasting infrastructure. So the trend this study models is less primary steel needed over time and more secondary recycled steel meeting the demand.
Okay, that makes sense. Less need to make steel from scratch if we recycle more effectively.
Right. But we'll still need some primary steel for a long time.
So putting it together, future demand, new technologies.
Yeah.
This study then looks at scenarios, doesn't it? Energy use, emissions.
Yep. 3 main scenarios to see how things could play out.
Walk us through them. There's a business as usual.
Yeah. BAU. That assumes we mostly stick with coal for primary steel, but the electricity grid gets cleaner over time, which helps the EAF recycling part.
Okay. Then the HDR scenario.
That one assumes HDR takes over completely for primary steel making by 2050, using green hydrogen, maybe some biochar too.
Full switch to hydrogen. And the third one, E1.
The E-wine scenario sees electrowinning deploying rapidly, starting in the 2040s, becoming the main primary route, with HDR acting as a kind of bridge technology before E1 fully ramps up.
Right. And the energy implications in these scenarios must be pretty dramatic.
Oh, absolutely. The study projects the energy demands for each. The big takeaway is electricity demand just skyrockets in the HDR and E-to-1 scenarios.
Because of electrolysis and the E-to-1 process itself.
Exactly. Huge jump in electricity needs. But on the flip side, thermal energy demand burning fuels drops way down. It's a massive shift in the type of energy needed.
Can you give us the numbers? How much electricity are we talking by 2050, say?
Okay, so the study projects by 2050, BAU needs about 1,100 terawatt hours.
Right.
HDR scenario, over 8,000 terawatt hours.
8,000, wow.
And the E-to-wine scenario, around 7,100 terawatt hours. Huge increases compared to BAU.
And that includes the electricity to make the hydrogen, too.
Yes, that's the total system demand for steel under those scenarios. By 2100, the numbers change a bit as recycling takes over more, but still very high electricity demand in the green scenarios.
And the CO2 emissions, that's the whole point, right?
Right. And here the projections are really promising. Both the HDR and EWN scenarios show pathways to get very close to zero emissions from steel by 2050.
And near zero by 2050, that's aligned with climate goals.
Exactly. Even the BAU scenario shows significant reduction, mostly due to that assumed grid decarbonization and more recycling, but nowhere near zero like the others.
Okay, a massive energy system transformation needed. How does the study see this playing out geographically? Does China stay dominant?
The analysis suggests that, at least initially, the energy demand distribution will probably follow current production patterns. So yeah, China remains a huge center for steel energy demand.
The sheer scale of electricity needed in China under HDR or EWN must be astronomical.
It really stands out in the study's regional breakdown for 2050. But the study also hints that peak energy demands and technology adoption might vary by region.
So potentially shifts in where steel gets made long term. Maybe places with abundant cheap renewables gain an advantage.
That's certainly a possibility implied by the energy shift, yeah. Access to cheap, clean electricity becomes paramount.
Okay, let's talk economics. Green steel sounds great, but is it affordable? This study looks at costs, right? LCOCS.
Yes, levelized cost of crude steel. It compares the traditional BF-BOF with HDR and E-wine out to 2050.
And what drives the cost competitiveness?
2 main things, according to this analysis. The price of electricity and the cost put on carbon emissions.
Makes sense.
If electricity, especially renewable electricity, gets cheap enough, and if there's a meaningful price on carbon making the old way more expensive, then HDR and E-to-1 start to look really competitive.
And the study expects renewable electricity costs to keep falling.
That's a key assumption, yeah. That trend is crucial for making these pathways economically viable.
What about just recycling steel in an EAF? That's the cheapest.
Right. Yes, direct EAF recycling is projected to remain the lowest cost route. But again, you're limited by how much scrap is actually available. You can't just build more scrap.
Good point. So for primary steel, it comes down to electricity and carbon prices.
Largely, yes. The study's cost breakdown shows that fuel, operating costs, and especially that GHG emissions costs for BF-BOF are huge factors.
And EWI, even if it has higher upfront investment costs.
The study suggests that because it's potentially more energy efficient overall, if those initial capital costs, CapEx, come down with scale and learning, EWI could actually become very cost-effective long-term.
Interesting. Higher efficiency paying off down the line.
Potentially, yes.
Okay, one last major impact point from the study. Hydrogen demand. If we go the HDR route especially, the need for green hydrogen is going to be massive, right?
Absolutely enormous. The study quantifies it for 2050. In the HDR scenario, we're talking somewhere between roughly 2,800 and 4,400 terawatt hours of green hydrogen needed just for steel.
Just for steel. How does that compare to, say, total global hydrogen projections?
Well, when you put it alongside IEA projections or think about hydrogen needs for other sectors, cement, chemicals, transport account, it becomes clear that decarbonizing industry, with steel as a huge part, implies building a truly massive green hydrogen economy,
Which means
which means vast amounts of new renewable electricity generation capacity and equally vast amounts of electrolyzer capacity to make the hydrogen. It underlines the interconnectedness of these industrial transitions with the energy sector transformation.
wow. Okay, so wrapping this up, this deep dive into trends in the global steel industry, evolutionary projections and defossilization pathways through power to steel paints a, well, a challenging but ultimately hopeful picture.
I think so, yeah. It shows that a zero-emission steel industry is technologically conceivable through these power-to-steel routes, HDR, EW1, plus really maximizing recycling.
And coupling it all with a clean energy system.
Absolutely essential. But as the study makes clear, it's not just a tech swap. It's fundamental shifts in technology, in energy infrastructure.
And maybe even where steel gets made.
Potentially, yes. Big transformations across the board.
What's fascinating, really, thinking about this study, trends in the global steel industry, is just how tied together everything is. Greening steel isn't separate from greening energy. They absolutely depend on each other.
Completely intertwined. One can't happen without the other, really.
So that leaves us with a final thought for you, our listener. Thinking about this huge transformation needed, this deep link between steel and energy. What do you see as the biggest hurdles? Is it still the technology? Is it the economics, the sheer cost? Or is it more about politics, getting the policies right, the international cooperation?
Yeah, where are the main roadblocks? Technological, economic, political, and crucially, what role can policy really play to speed things up, to make sure this transition actually happens at the scale and pace needed?
Definitely something to think about. We really encourage you to check out the full source, Trends in the Global Steel Industry, Evolutionary Projections, and Defossilization Pathways through Power to Steel. Dig deeper into these questions and consider what it all means for other big industries trying to go green.